This is a brief presentation about theory, sensors, sensor maintenance and measurement of the pH value of a sample. During this presentation, a brief overview of pH theory and measurement of pH values is given. We look at the chemical background of the pH value, at the electrodes which measure pH values, and how to use these electrodes. So what is pH? pH is a definition of how acidic or alkaline a solution is. For human beings, the taste of acid can be bitter, unpleasant, and sometimes even inedible. Why is something acidic? Acidity is caused by an excess of hydrogen ions in a solution. Normally hydrogen ions react with hydroxide ions to form water, but if an excess of hydrogen ions are present, a solution becomes acidic. The hydrogen ions are released into the solution through dissociation of a chemical substance called an acid. Some of the most well-known acids are hydrochloric acid, sulfuric acid and acetic acid. The last one is better known as vinegar. The dissociation formulas of some acids are shown on the slide. The whole pH range includes both acidic and alkaline pH values. The scale for pH is defined from 0 to 14, where pH values from 0 to 7 are in the acidic range, and pH values from 7 to 14 are in the alkaline range. The pH value 7 is neutral. On the slide, some examples of samples are given for the whole range of pH values. The upper examples are for everyday products that we experience in our own lives. The examples below the scale are for pure chemicals. For daily use, article pH values in the range of pH 2 to pH 10 are common. We do not generally come into contact with products with more extreme pH values than these. The other end of the pH scale from the acidic one is the alkaline one. These are the pH values between 7 and 14. At this end of the scale, the hydroxide or OH- ions are present in excess. Solutions with these pH values are created by dissolving a base in an aqueous solution. The base splits up to release hydroxide ions and causes the solution to become alkaline. Some of the best known bases are sodium hydroxide, ammonia and carbonate. The next question to be answered is, what does the pH value actually mean? Physically speaking, the pH value is defined as the negative logarithm of the concentration of hydrogen ions in the solution. The formula for this is shown in green on the slide. What this translates into in daily life is that for a solution with a hydrogen concentration of 0.1 mole per liter, the pH value is 1, since the negative logarithm of 0.1 equals 1. For a solution with a hydrogen concentration of 0.001 moles per liter, the pH value is 3. For the whole range of pH values from 0 to 14, the concentration of hydrogen ions therefore varies from 1 mole per liter to 10 to the power minus 14 moles per liter. Why do we have this range of numbers from 0 to 14 for the pH value? This is because of a certain physical property of water. In water of 25 degrees Celsius, the concentration of hydrogen and hydroxide ions are related in such a way that the product of the two is always 10 to the power of minus 14. This relationship between the hydrogen and hydroxide ion concentration is shown by the second equation on the slide. Because of this relationship, we can find out the concentration of one if we know the concentration of the other, if we measure at 25 degrees Celsius. So for example, if the concentration of hydroxide is 10 to the power of minus 7, also the concentration of the hydrogen must be 10 to the power of minus 7, since the product of both needs to be 10 to the power of minus 14. Since both are present in equal amounts at this concentration, we then have a neutral solution at this concentration of hydrogen ions. This means that on the pH scale, a hydrogen concentration of 10 to the power of minus 7, which is equivalent to pH value 7, is neutral. This is what we know from daily experience, like advertising of shampoos. Up to now we have seen some examples of pH values for certain products and also how we define the pH value. The next question must be why you want to know a pH value of a certain product. Well, it is for example important to know the exact properties of product when it is manufactured. Also, the pH during the production can be important if the reaction that has to take place has an optimal pH value. When this value is not reached, the reaction will be much slower or have a lower yield, and the final product will become more expensive. Also, for the environment or for people, some pH values are not healthy and contact with these should be avoided. This is often also demanded by regulatory requirements. An important reason as well is the fact that most equipment and instruments are susceptible to products with very high or very low pH values, which can cause them to wear out much faster or break down completely. There are several industry areas where these measurements are important. For example, in environmental and water utilities for determination of the pH value of streams and rivers, and for quality control of tap water. Also for industrial wastewater, which will be released back into the environment, it is important to know the pH value. Now that we know how the pH value relates to the chemical composition of a solution and why it is important to know this composition, we still need to find out how we can determine the pH value and with which instruments. The principle of pH measurement is that one takes a sensor with a glass membrane which is sensitive to hydrogen ions, and that this sensor therefore shows a certain reaction to the sample solution. To be able to use this reaction in a quantitative way, a second sensor is needed as well, the so-called reference sensor or reference electrode. This electrode is not responsive to the sample solution and has therefore a constant potential with regard to which the measurement sensor potential changes, depending on the amount of hydrogen ions in the solution. The potential between the two electrodes is therefore a measure for the amount of hydrogen ions in the solution and thus for the pH value. In the slide, a measurement setup with a sensing electrode and a reference electrode in the sample solution can be seen. The potential difference between these two electrodes changes in a defined way as a function of the hydrogen concentration and therefore the pH value. This relationship between the potential and the concentration of hydrogen ions is given by the Nernst equation. The Nernst equation consists of several physical constants and the temperature of sample and electrode. If all the physical constants and a standard temperature of 25 degrees Celsius are input into the equation, the relationship between potential and pH is a potential change of minus 59.16 millivolts per pH unit. So if the pH value increases from 7 to 8, the potential decreases from 0 millivolts to minus 59.16 millivolts. This well-defined relationship between potential and pH and the sensitivity of the pH electrode membrane to hydrogen ions then enables us to measure the pH value of a solution and calculate the concentration of acid or base present in this sample. The measurement and reference electrodes are both constructed in a different way. The right electrode on the slide is the reference electrode, and this has the function to keep a constant potential in any solution. To be able to do this, it can release ions from the reference electrolyte into the solution through the diaphragm. This is drawn at the bottom of the electrode. It also has the reference system inside to release ions and a filling port to exchange or top up the electrolyte solution. The pH measurement electrode is drawn on the left side of the slide. This electrode is close to the outside world and only reacts to the diffusion of hydrogen ions into the gel layer around the membrane glass at the bottom of the electrode. It also has an internal solution and a platinum wire inside. Both these electrodes are connected to the pH meter, and this meter detects the potential of both electrodes and calculates the difference between them. This gives the information about the pH value. This is how the measurement of pH values with electrodes was done originally, but since this needed two measurement electrodes in the sample, a simpler solution was found in the combination pH electrodes, which we will see later on during this presentation. All modern reference electrodes are based on the silver chloride reference system, and with this system there are two different ways to implement it. The simple way is to use a wire coated with a thin layer of silver and silver chloride. The disadvantage of this system is that the silver ions will go off the wire during measurement, and therefore the solution around the wire has to be saturated with silver ions to make sure that the wire remains coated with silver chloride to make further use possible. Should the wire be allowed to get blank because no saturated silver solution is present, the electrode cannot be used anymore. The second system is a bit more advanced, and this does have a silver chloride cartridge that has a silver depot to make sure that the silver released by the reference element doesn't run out, and that the reference element can function for a long time. Because there is no danger of the silver running out in this design, it is not necessary to have silver chloride saturated KCl as a reference electrolyte. One can just take a 3 molar solution of potassium chloride without any silver. The combined pH electrode was developed in the 1940s of last century and is a combination of a reference electrode and a pH electrode into one combined electrode. In the drawing it can be seen that the pH electrode is the center section of the combined electrode, whereas the reference element is the outer part of the pH electrode. This has the ceramic junction diaphragm on the side for contact between the sample solution and the reference electrolyte. The inner part, which is the measurement electrode, also has a temperature sensor in this specific electrode, which is labeled in the drawing. Also, the other components are labeled. Another important item for the reference part of the combined electrode is the filling hole to top up or exchange the electrolyte solution. This filling opening has always to be opened during measurements for a constant potential in the reference electrode. If the opening is closed during measurement, the reference electrolyte cannot flow freely out of the electrode and the potential cannot be maintained at a constant value. A consequence of this is that the measured pH value will be fluctuating and the measurement will be wrong. Mettler-Toledo manufactures a lot of different pH, reference and combined pH electrodes. The reason for this is the fact that different samples need different properties in the pH electrode to get the quickest and best results. The parts which are important in this respect are the shape of the membrane glass, whether or not a temperature sensor should be present, which reference system is present in the electrode, and the material of the outer shaft which will be in contact with the sample during measurements. Also, the reference electrolyte solution is of interest, and the junction or diaphragm through which the reference electrolyte has to flow out into the solution. To start with, we have a look at the type of junctions which are available for the electrodes. The default diaphragm is the so-called ceramic frit. This is a small insert into the shaft of the electrode which is made out of porous ceramic material which allows the reference electrolyte to flow through it. For most applications, this is a good solution as it allows a free flow and contact between the inside and outside of the reference elements. The electrolyte flow through the ceramic frit is relatively slow at approximately 1 milliliter per 24 hours. The disadvantage of this junction is that it can quite easily clog up if the sample solution has particles in it or if it is very viscous. In this case, the second type of junction available is a better solution, the ground glass junction with a movable sleeve. This is a junction which has a sleeve over an open hole in the electrode shaft and which therefore cannot be blocked by a viscous solution or by small particles present in the sample solution. Because of this open connection between inside and outside of the reference element, the flow of the electrolyte is a lot faster than with a ceramic junction. The flow of electrolyte with a sleeve junction is approximately 4 milliliters per 24 hours. In the slide, two example photographs can be seen. The standard ceramic frit electrode, the InLab 412 on the left, and the InLab 420 on the right with the ground glass junction. A third option for the junction is the open junction, which has no barrier between the inside and the outside of the reference element. As you can imagine, this is only possible if the inside of the electrode is a solid polymer electrolyte. Because of this solid polymer, the flow of the electrolyte can be controlled during the measurement and no complete loss of the electrolyte solution takes place. In the drawing, an InLab 430 electrode is shown with its open junction in the bottom of the electrode, next to the glass membrane sensing part. The temperature sensor also sticks out of the bottom, right next to the pH membrane, so that the measured temperature is always the correct one. In a close-up of the junction, it can be seen that the polymer solid-state electrolyte is in direct contact with the solution and can thus exchange ions with the solution to maintain a stable reference potential. This junction is usually used for very dirty samples like soil suspensions or equivalent. The type of diaphragm is also a very important factor in the choice of a pH electrode, as a blocked diaphragm is the main cause of wrong or unstable pH measurement. The sample itself can cause blockage of the junction if the solution contains, for example, proteins which can get stuck in the porous ceramic material, or if there are small particles in a suspension which can nestle into the porous ceramic junction. Also, oily samples can block the diaphragm through their viscosity. Another reason why the diaphragm can be blocked is if a chemical reaction takes place between the inner electrolyte of an electrode and the sample solution outside the diaphragm. This can happen if there are, for example, sulfides present in the sample and silver ions in the reference solution. When the two meet inside the diaphragm, the silver ions and the sulfides will form solid silver sulfide, and this will block the junction. Another important part of the pH electrode is the reference element. Ideally, this shouldn't cause any precipitation of molecules if the ions of the reference element and the solution meet each other. One way to achieve this is to use a reference element with an ion trap. Toledo has developed the Argentile silver ion trap for this purpose. The Argentile ion trap stops the silver ions from getting into the inner electrolyte solution and therefore from diffusing into the diaphragm, where ions in the sample could react with it and the complex could precipitate. It is very important to have the Argentile reference element in an electrode used for samples containing chloride or sulfide, as these would react with silver ions to give an insoluble precipitate and block the diaphragm. If it is not clear whether or not the sample contains ions that will precipitate with silver ions, one can mix a bit of the sample with silver-containing electrolyte to see if a reaction takes place. If this is the case, then a pH electrode with the Argentile reference system is necessary to keep the silver ions away from the diaphragm. A detailed drawing of the elements of this reference system is given on the slide. The next item, which is important in the choice of electrode and is related to the type of junction used, is the choice of the reference electrolyte. The first type of reference electrolyte is the liquid reference electrolyte. This has a fast response because of the fast flow through the junction. It is also accurate and can be used for extreme pH value measurements. The lifetime of electrodes with liquid reference electrolyte is relatively long, as the electrolyte can be exchanged and topped up to prolong the electrode lifetime. This immediately is also the disadvantage, as this means that the electrode maintenance is required. Also, the glass used for these types of electrodes can break and make the electrode unusable. In this respect, the gel electrolyte is better, as this is maintenance-free, simply because the electrolyte cannot be refilled, which also makes the electrode a disposable item. But because of this, the electrode is robust too. The disadvantage of the gel electrolyte is that the electrode response is slower than for the liquid electrolyte, as it doesn't flow that fast. The third alternative is a solid electrolyte, which is also slow and cannot be refilled. This then also means that the electrode is maintenance-free and disposable, but that the diaphragm cannot be clogged up. The shaft material of the electrodes is another important property. Different ones available being glass, polysulfone, PEEK and epoxy. With these available options, the main choice is glass or plastic. If this choice has been made, different kinds of plastic can then be chosen to suit the application. All plastic shafts have in common though that they are not suitable organic solvents, so for measuring these a glass electrode is obligatory. The glass electrodes always have liquid electrolytes. Plastic ones can have a variety of electrolytes. When the sample measured is not at room temperature or is at varying temperatures, a temperature sensor is very useful to perform an automatic temperature correction of the measured pH values. The temperature can be measured with a separate temperature sensor in the solution, which can be connected to the pH meter. but also with an integrated temperature sensor in the pH electrode itself. This can be done with multi-pin connection pH electrodes, which have connections to the meter for the reference and pH electrodes via a BNC connector, and for the temperature sensor with a chinch connector. There are also electrodes available with a fixed cable to the electrode and a BNC chinch on the meter side. Built-in temperature sensors are available as PT1000 or as NTC. A separate temperature sensor can also be used again. Toledo has either PT1000 or NTC options available. Shape of the membrane is important for the reaction of the electrode to the solution. If the membrane is spherical, it is more resistant to contraction at low temperatures and therefore suited to low temperature measurements. An example of this is the InLab 428 electrode, which is shown on the leftmost photograph in the slide. The hemispherical membrane pictured next to it is ideal for small sample volumes, as the whole membrane is in the lower part of the electrode and can be immersed in relatively small sample volumes. On the photograph, the InLab 422 electrode, which is a semi-microelectrode, is shown. The rightmost electrode on the slide, the InLab 429, has a cylindrical membrane glass. This cylindrical shape has the advantage of giving the membrane a larger surface area. Because of this higher surface area, it has a lower membrane resistance and is therefore more suitable for ion-poor solutions like pure and ultra-pure water. Apart from these more or less standard membrane shapes, there are also a few special membrane shapes, which have been developed for specific applications. One of these is, for example, the spare or puncture electrode, which is made specifically for solid or semi-solid samples like food items such as cheese and meat. A picture of this is shown in the left picture on the slide. There is the microelectrode, which is suitable for test tube measurements and shown in the middle photograph. Also, for flat surfaces like skin or paper, a special electrode has been developed, which is shown in the right photograph on the slide, and has a flat membrane surface for optimal contact with the flat samples for which it has been developed. So in a sample, what does one have to be aware of to make the right choice of P electrode to measure it? One has to know if the sample is clear or a suspension, if it is viscous, what are the components in the solution, and what are the temperature and expected pH range of a sample solution. Also, the amount of sample is important and the sort of container in which a sample has to be measured. The materials the electrode shaft and membrane glass are made of are important with regard to the solvent used, and also the shape of the membrane has to be taken into account. A few examples of the relationship between sample and pH electrode properties are given in this slide. If a sample is clear, the ceramic junction is a good choice for the electrode, but if the sample is dirty like a suspension, an open or sleeve junction is better. The consistency of the sample is important too. If the sample is a non-viscous liquid, any type of junction will do, the standard ceramic junction will work fine. If the sample is an emulsion, an open junction is best. If it is viscous, a sleeve diaphragm can best be used. For suspensions or slurries, either a sleeve diaphragm or an open junction can be chosen. For semi-solid samples, a puncture electrode is needed, and for flat, solid surfaces, the flat membrane electrode must be used. Other examples of samples are low ionic strength samples like deionized water, which benefit from double bridge electrodes with low membrane resistance. For high ionic strength samples with high pH value, high alkali glass is important. For samples with sulfides or proteins, a silver ion trap is important. Samples with non-aqueous solvents need a special electrode with a sleeve diaphragm and high electrolyte flow. For hydrofluoric acid, a purpose-built electrode is needed, the InLab 429, which can measure solutions of hydrofluoric acid up to 0.1 molar concentrations. Does the customer want to measure temperature with the electrodes as well, and what is the pH range they are interested in? After the general theory and composition of the pH measurement electrodes, we now have a look at how to treat these sensors which can measure the pH value of a sample. The important factors for pH electrode lifetime optimization are cleaning, maintenance, storage, and possibly regeneration of the electrode. The electrode should always be stored in either the electrode electrolyte, like 3 molar potassium chloride, in pH buffer solutions 4 or 7, or in a diluted hydrochloric acid solution of approximately 0.1 mol per liter. These solutions are rich in ions and water and will not dry out the pH-sensitive glass membrane of the pH electrode. If the electrode is stored in distilled water or even completely dry, the membrane glass and the gel layer around it are affected strongly, and the lifetime of the electrode will be shortened drastically, or it will even be destroyed. Also, with this kind of storage, the electrode is never ready for immediate use and has to be conditioned before every measurement, as the gel layer around the glass membrane first has to be built up and regenerated again. When using a glass pH electrode or any other pH electrode with liquid reference electrolyte, the electrolyte has to be exchanged or topped up regularly, for example every 2 weeks. It's also important that the reference electrolyte level is higher than the sample solution and that the filling hole needs to be open during the measurement, since the sample solution would otherwise flow into the pH electrode instead of the reference electrolyte into the sample solution. What one also has to be careful about is that there are no air bubbles in the electrolyte near the junction, as this would also restrict the electrolyte flow. Just shake the electrode like a fever thermometer to get rid of these bubbles. In standard pH electrodes with an argentile reference system, the electrolyte solution for non-aqueous solutions is a 3 molar solution of potassium chloride. In non-aqueous solution, it should be a 1 molar solution of lithium chloride in ethanol. Again, you can check for precipitation reactions by mixing sample and electrolyte. If you don't see a fallout, the combination of the two is okay to use. Most measured samples are in watery solutions, but sometimes customers will want to measure the acidity of non-aqueous solutions. Examples of this can be the measurement of more or less pure acids, alcohols, and mineral or edible oils. To measure these solutions, which are generally ion poor, an electrode with a sleeve diaphragm and high electrolyte flow is necessary. Since these solutions are water-free and ion poor, the electrode needs to be reconditioned between every few measurements in water for approximately 5 minutes to regenerate the gel layer around the glass membrane. Overnight, the electrode needs to be regenerated in ion-rich aqueous solutions like diluted acid, pH buffer 4, or potassium chloride solution to hydrate and regenerate the membrane. As with all electrodes, it will need regular new calibrations, at least every morning before commencing measurements. The cleaning of the electrode is generally done by rinsing with deionized water and shaking off excess water before measuring again. If necessary, the water on the glass shaft may be dabbed off with a paper tissue. Never wipe the glass membrane dry with a paper towel, as this will damage the pH-sensitive membrane and may make reliable measurements impossible. The cleaning of the diaphragm is also a very important maintenance task, as a blocked diaphragm will make measurement impossible. As we saw before, the diaphragm can be blocked if a reaction between sample and electrolyte takes place. This can happen with either chloride or sulfide in the sample solution. Chloride forms silver chloride, and this can be cleaned with a concentrated ammonia solution. The sulfides form silver sulfides with the silver from the reference electrolyte, and this can be removed again with an 8% thiourea solution in 0.1 molar hydrochloric acid. Should the diaphragm be blocked with proteins, a 5% pepsin solution in 0.1 molar hydrochloric acid can be used to clear it again. For all other contaminations, an ultrasonic bath can be used to clean or unblock the diaphragm. After cleaning, the pH electrode should of course be calibrated again before any measurements. Mettler-Toledo supplies some of these cleaning solutions ready to use. The part numbers are also given on the slide as a reference. Should the electrode not work properly anymore despite all cleaning, storage and maintenance activities, it may still be saved by reconditioning of the glass membrane. If the electrode by accident has been stored dry, put it in a 0.1 molar solution of hydrochloric acid for 12 hours and try if it is possible to get a good calibration from it. If the electrode is still out of the specifications after this, or if it was out of specs without being kept dry, it may also be possible to recondition the membrane with a regeneration solution which can be bought via Mettler-Toledo. This solution contains hydrofluoric acid and is very aggressive. It eats away part of the glass membrane and brings a fresh layer of the membrane into contact with the solution. When using this solution, be careful not to leave the electrode in this too long, otherwise the whole pH-sensitive membrane is eaten away and the electrode doesn't react to the sample anymore at all. Again, after these regeneration steps, the electrode needs to be calibrated before use. Taking into account that the electrode is maintained in the proper way, stored correctly, and mainly used in aqueous solutions with a pH range of 1 to 12, the expected lifetime should be between 1 and 3 years, depending on the frequency of use. This is valid only for room temperature use. At higher temperatures, the lifetime decreases proportionally. This can also be seen in the table on the slide. Now that we have seen what the pH theory is, how the equipment technically works, and how it should be handled between and before use, we finally get to see how to actually perform a measurement and the required calibration to get a reliable result. The accuracy that can be reached with a pH electrode depends on how we measure with it and how the preceding calibration was performed. In general, we can say that the main influence on the measurement accuracy are calibration, temperature, and the electrode type. The calibration procedure needs to be performed regularly, but at least every day before measurements are started. The procedure should also be performed correctly, according to the instructions, and fresh and accurate buffer solutions should be used. The temperature is important as well, as one should be aware of any differences in temperature between calibration and measurement solutions. Also, for the temperature of the sample and its temperature dependency with regard to pH value, it's important to know the temperature. The temperature dependence of the pH electrode can be corrected by the meter. The sample variations are sample specific and cannot be accounted for by any pH meter. The last factor in determining the accuracy of the measurement is the electrode itself. It should be a suitable electrode for the kind of measurements one wants to perform, and the diaphragm should be clear during the measurement as well. All in all, an accuracy of plus minus 0.05 pH units should be achievable. Generally, we incorrectly use the term calibration for electrode adjustment. In principle, this is not 100% correct, as a calibration is only a check if the electrode is working properly. Usually you have to change some settings in the meter after this calibration, and this is what we call adjustment. So what exactly is this adjustment of an electrode? The adjustment is the checking of the electrode millivolt values with known solutions, so-called pH buffer solutions. These solutions can be bought commercially and have a guaranteed certified pH value. This value is input into the pH meter when the electrode is immersed in the solution, and this is the adjustment. For example, on the slide in orange, the ideal pH dependence of a pH electrode is shown. But after the calibration, it shows that the ideal 0 millivolt value for pH 7 is not found with the tested electrode. Then the offset value for this electrode is transferred into the meter, and this is called the adjustment. This is only the offset from 0 millivolt adjustment. The slope can also deviate from the theoretical value, which we saw earlier, and which was 59.16 millivolts at 25 degrees Celsius. For a slope adjustment, we need to have more than one pH buffer for calibration though. With the second buffer, we have 2 points on the graph, which makes it possible to determine the real slope of the electrode tested. If we have 1 millivolt value for pH 7 and another for example, pH 4.01, then we can take the millivolt difference and divide this through the 2.99 pH units difference between the two tested points and find the real slope or millivolt per pH unit dependence of the electrode. Again, in the slide, the orange curve shows the ideal theoretical electrode behavior, and the green curve shows the adjusted slope for the real behavior found for the electrode. For the calibration and adjustment to be able to be performed correctly, the right solutions to test with are very important. The buffer should always be fresh and can only be used once. After first use, there is no guarantee for the correct pH value of the buffer, as it is never certain what it has been contaminated with. When using a bottle for the buffer solution, always make sure to only pour solution out of the bottle and never back into it. Keep the bottle closed when storing it and keep it in a cool, dark place. After every calibration point in a buffer solution, clean the electrode and only then put it into the next buffer solution. Also be aware of the temperature of the buffer and use the automatic temperature compensation to make sure that the correct pH value for this buffer at this temperature is used from the table in the pH meter. This lookup table is used automatically in the meter when the settings are on automatic temperature correction and if the buffer settings are set to the standard buffer groups. So when do we need to adjust the electrode? For standard use with easy samples, it should be adjusted at least every day before measurements are begun. With more demanding samples, which are dirty or non-aqueous, the adjustment needs to be performed more frequently. Also, if the accuracy should be very high, the adjustment should be performed more often than when accuracy is not so important. With older electrodes, the adjustment also needs to be performed more frequently. When an electrode is treated with certain procedure, it always needs readjustment. Some of these procedures are the replacements of the electrolyte, the cleaning of a blocked diaphragm, after storage, after regeneration, etc. One important issue for correct measurement is to know what the temperature of the sample is and to correct for both the buffer value at that specific temperature and the slope of the electrode at that temperature. The buffer value temperature dependence is available from a temperature table programmed into the pH meter. The slope correction for the electrode temperature dependence is also programmed into the meter with the Nernst equation. In the slide, some examples for the slope at certain temperatures are given in a table and a few slopes are drawn into a graph as an illustration of the dependence. As can be seen, the temperature dependence is quite big and cannot be neglected even for only a few degrees temperature difference. Please be always aware though that the pH meter cannot compensate for the temperature dependence of the sample itself. For example, sodium hydroxide has a different pH value for a concentration of 0.001 moles per liter at 20 and 30 degrees Celsius. At 25 degrees the value is 11, as can be found from the pH equation, but at 20 degrees the pH value is higher and at 30 degrees the pH value is 0.17 units lower. This dependence is different for every chemical compound and solution and can therefore not be taken into account by the meter, as the meter cannot know what sample and composition it is measuring. Still, it is important to record the temperature during the measurement, as this is necessary to make comparisons afterwards. As a summary, the pH meter does compensate for the temperature dependent slope of the pH electrode, but not for the temperature dependence of the sample. The only exception to this last rule is for the standard buffers where a temperature table is programmed into the meter for a certain temperature range. This is a lookup table and not an equation, which would make it possible to calculate the dependence over the whole temperature range. As a brief summary of what one should and shouldn't do with pH measurement, a few troubleshooting points and some things that you absolutely shouldn't do with a pH measurement are given. What can be the cause that an electrode is not performing well is that the membrane is dehydrated, contaminated or damaged. Also, the electrolyte can be missing or contaminated with another chemical. There can be air bubbles behind the ceramic junction or behind the membrane. The junction can be blocked or contaminated, or crystals from the reference electrolyte can be interfering. Another possibility is that the electrode is just worn out and should be replaced. What should never be done during a pH measurement is to keep the filling hole closed when measuring. The electrode should never be stored in deionized water or the membrane wiped clean. It should be calibrated often enough and temperature influence needs to be taken into account. The electrolyte should be changed regularly and one should be aware that there are things which can go wrong with pH measurements. Never take the measurement for granted.